This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Podker. From rainbows to why the sky is blue, light catches the imagination and raises questions from an early age. Isaac Newton established our visible spectrum in the 1600s, and in the 1800s, James Clerk Maxwell mathematically linked light to electromagnetic waves. In the early 20th century, Albert Einstein's description of light was central to his theory of special relativity, and this description of light in quantum mechanics would lead to the development of lasers. Today, lasers are used for scientific, medical, defense, and industrial research, such as novel particle accelerators, advanced radiological tools, and industrial diagnostics. Our guest today is Franklin Dollar, Professor of Physics and Astronomy and Associate Dean of Graduate Studies in the School of Physical Sciences at University of California, Irvine, who explores the physics of ultra-fast lasers in his work. Professor Dollar, thank you for joining us today.
Absolutely. Thank you for having me.
So I'd like to start with a little bit of the background, and I'd like to ask you how you first got interested in lasers.
Yeah, sure. So I would say that I became interested in light before I became interested in lasers. When I was in undergrad, I participated in an MSF research experience for undergrads that was connected to a engineering research center. So this was the Extreme Ultraviolet Engineering Research Center that had just formed, and I was able to go ahead and participate. And I worked at the a facility at Lawrence Berkeley Labs called the Advanced Light Source. And I previously had not done any research experience or really even understood what physics really meant as a career option. And so going from working at a job stacking boxes and cashiering to something like working at a giant particle accelerator to make light was a pretty big, it was a pretty big transition and really fun one. And that really was how I first became interested.
It captures the imagination when it's tangible and you're like in the space.
And it ages me a little bit, but at the time they made the first Hulk movie by Ang Lee, and they filmed it at that actual facility. And so it was literally going into a place that science fiction occurred in the real world.
I want to set up, you mentioned extreme ultraviolet light, and I'd like to set up a kind of definition for people that don't know what that means.
Yeah, it's a very strange region of the electromagnetic spectrum. So we have visible light, and we all have these great detectors in our head that allow us to see visible light. And then we maybe have some familiarity with infrared, kind of on the more red side of the spectrum where we can't see, but we can feel it quite well. And then ultraviolet on the other side of the spectrum, higher energy light or smaller wavelengths than the visible spectrum. And that gives us sunburns and things like that. Extreme ultraviolet sounds like a really hardcore version of ultraviolet light, and it is. It's a more energetic version of light. But we don't hear it used that much colloquially. And one of the reasons for that is because it's actually a very difficult region of light to work with. Because nearly everything in all matter absorbs very strongly in this wavelength region. So if you made any kind of light like this, very quickly, air, glass, plastic, water, anything will just absorb this light very, very quickly. So if you did manage to make some, you probably couldn't use it very easily. The X-rays, on the other hand, we learned how to make, and they just pass through everything. And we were able to use those successfully in science for quite some time. Now, with extreme ultraviolet light, that weakness also ends up being great strength because everything does absorb it, but it absorbs it in a slightly different way. So you can see how copper absorbs it and see how that changes from carbon and how that changes from oxygen. And suddenly you get every element absorbing this light differently. And that allows you to do some very interesting chemical studies, for instance, or microscopy, where you can see how the different elements that make something up are are absorbing that light, and then you can make an image out of it. Probably the thing it's most well known for is the fact that as we pushed Moore's law farther and farther in making smaller computer chips, we've actually gotten to the point where using regular lasers and ultraviolet lasers can't make small enough features. So we need smaller wavelengths of light to make smaller computer chips. And so the ultraviolet lasers we used before just can't make smaller features. And so we had to go to the extreme ultraviolet to make state-of-the-art computer chips. And so if you have your latest smartphone, these have computer chips in it that were almost certainly made using extreme ultraviolet light because it's wavelengths of several nanometers to tens of nanometers, so much, much smaller than what we were using previously in the hundreds of nanometers, which is where ultraviolet light would be.
So as you're studying extreme ultraviolet lights, how are lasers being used? What are the benefits of using that source?
So we can think of different ways of how we even make light. And if we make very early on, man can make light by making a fire, and it would be hot and produce this light. And that was very good for everyone at the time. And we have more advanced ways of making light now, but essentially it's a way of taking matter that has some energy that's put into it and having that energy come out. And for a lot of the light sources we use, whether it's this light bulb that's illuminating me or the screen of my computer, the energy that gets released is not that energetic. The photons that come out are having energies that are very moderate. Extreme ultraviolet photons have a much more energetic, are much more energetic and have a lot more energy per photon. And so we need to find ways of making matter radiate that light with much higher energies. And that ends up being a little bit more tricky. So some of the ways we're able to do that is to take matter and really perturb it to its core. And so trying to find ways of taking something like an atom and not just working with the electrons on the surface, but working with electrons that are much more tightly bound deeper into the surface of that atom, that are more energetically favorable for these types of things, is where we can make those things happen. And lasers are great because we can go ahead and deliver lots of energy into a very small volume to make these types of situations occur. And so, for instance, in the extreme ultraviolet example I talked about earlier for making computer chips, we take a little tiny droplet of tin, and by focusing a laser into that, we can concentrate that energy, making this tin droplet very, very hot, conditions that you would maybe see on a star or something like that. And then such a hot thing is no longer going to be just emitting light, say in the visible region where we'd see, but we can also make conditions that would make it favorable to make extreme ultraviolet light come out. And so that's one of the nice ways of using a laser to do this, because lasers can be made relatively cheap and you can move them around really easily. And then you're just manipulating the light to get to this little droplet of tin to make the extreme ultraviolet light that you need to make the computer chips.
As we head towards the big focus of our conversation here, I think we need to introduce plasmas a little bit and how lasers and plasmas and these things are coming together.
So when we have our laser and we're focusing it into matter, we're making it so hot, the matter itself is no longer going to stay in the same state of matter that it was as it started off with. So if I have something like a rock that I can hold in my hand, it has a temperature associated with it that's going to be something like room temperature. If I were to heat that rock enough, it could eventually melt. And that's kind of what we're doing with the laser a bit. We're increasing these temperatures to the point where now this thing is getting to a state where the matter is no longer staying in its same state anymore. But we're doing it in a slightly different way than, say, taking a piece of metal and melting it. We're actually taking these atoms that are inside of this material and we're pulling them apart. So we're taking the electrons and pulling them off of the ions that make up the atom. And so now we have something that is still like a liquid, like that liquid metal, but the electrons are no longer bound to the parent ions that they were before. So the electrons can kind of do one thing and the ions can do another. And what makes this very unique is that they have charge. So the electrons are negatively charged and the ions are positively charged. And now, instead of just having fluid dynamics control how this fluid behaves, we have Maxwell's equations and electrodynamics that come in that can also control how this fluid behaves. And when we have both of those at the same time, we call such a state of matter a plasma.
What brought your work to my attention was we recently have opened the Zeus Laser facility, and I believe you have the honor of being the first person to run experiments on it. So I would like to ask you what the facility is for the general audience, And then I would like to get into the experiment a little bit.
Absolutely. The Zeus laser facility is a 3 petawatt laser facility, where 3 petawatts is a number that maybe we don't hear very much, where usually we think about watts as a thing. So we have a 100-watt light bulb or something of that order. And this is a petawatt. So it would be like if you had a light bulb, over 1 billion even, or over 1 trillion even of these light bulbs, that still is nowhere close to having this petawatt of light power coming out of this laser system. So it's by far one of the brightest light sources we've ever created. And being 3 petawatts would put this as the most powerful laser facility in the United States. The Zeus laser facility is unique in that it's not just a really big laser, but you can also split parts of the laser off to do other unique experiments. So you can take 2 petawatts in one beam and 1 petawatt in another beam and interact them differently. So then the question will be, why do you need just such a crazy powerful laser that, you may want to mount on a Death Star or something like that? And the reason is because these are a very special class of lasers that we're building. They're what we call an ultra-fast laser. And it's enabled by a technology that won the 2018 Nobel Prize, chirp pulse amplification. And the amazing part of it is, even though this is a very powerful laser, there's actually not a lot of energy in it. And that's what allows us to make things that are just ridiculously powerful. Because, for instance, the US power grid is on the order of a terawatt. So at any given moment, there's a trillion joules per second going through the US power grid. And that's its steady state. We can achieve things that are 3,000 times higher than that. But the trick is we only do it for a very little amount of time, because power is more of a rate than it is an absolute. So with a little bit of energy, we can create some of the most intense conditions known in the universe. We pull these electrons off, and the laser is so intense that these electrons are now accelerated to close to the speed of light. So now Einstein enters the picture. We have the theory of relativity, and relativistic mechanics is now being added to my electrodynamics and my fluid equations that I had before. So it's a very complicated interaction that's occurring here. And because of the extreme, I'm using extreme a lot today, but this very much warrants it. It's such an extreme interaction that, again, like you can really only see in some of the most extreme areas of the universe, that this can potentially create new light sources and new particle sources that we can then harness for use in a variety of applications, as well as teaching us about the underlying physics of how intense light can interact with matter, perhaps giving us insight into some of these extreme events that we see around the universe.
Right. Gives you a real tangible or measurable right now happening, as opposed to something in space that maybe you're getting the information right even.
Yeah, it's a lot easier to be able to do experiments in a laboratory. And if you're trying to investigate something like a galactic nuclei, it's a lot more difficult to go ahead and visit that as currently.
Can you tell me a little bit about what the experiment you're running is now?
Yeah, so we are performing kind of what is more close to one of the flagship experiments of the Zeus facility. So part of it is an electron accelerator, and we do this by focusing our light into a puff of gas. And when the laser is going through this puff of gas, it's turning it into a plasma and making a wave. So this plasma wave that exists, but it's an extreme wave. And what happens physically is very similar to what you'd see if you had a big boat going real fast out on the water. It pushes the water out of the way and basically makes its own wave as it propagates through. So you can imagine you could have someone behind the boat with a little wakeboard, and they can go ahead and go down that wave that was created, gaining more and more energy until they eventually end up just as fast as the boat. This happens in our plasma wave as well, but instead of a little person on a wakeboard, we have an electron. And the electron can roll down this plasma wave and basically get to the same velocities as the laser pulse itself. And so we can accelerate electrons to very, very high energies, comparable to those that we normally would see at large particle accelerators that we've built in the past. The difference is this is all happening in a laser focus. So in something like the length of a centimeter, I can bring electrons to energies that would normally take me particle accelerator the size of a football stadium to create. And so this is not just compacting our particle accelerator, but using a new type of plasma wave to accelerate it. And so this is called laser wake field acceleration. And it's been a relatively successful application of laser matter interactions in making an advanced accelerator that uses light and matter to accelerate the particles, as opposed to using our more traditional particle accelerator technologies. The experiment that we were looking at is how such an accelerator can also make light. Because if I have an electron and I accelerate it, that accelerated electron will make light. And in some cases, this is something that we maybe take for granted. When light passes through something like a window, it's actually passing through a lot of matter. And these electrons will oscillate up and down with the same wavelength as the light that's hitting it, and they'll make light that's the same color as the light coming through it. And so we don't even notice this light passing through the window. So in our plasma wave, these electrons are going through the plasma wave, and they're really being shaken up and down quite violently. And that's not going to create just regular visible light, but can create X-rays as well. So now we have this electron that's moving along. We're making it relativistic. We're bringing it to very close to the speed of light, but we're also wiggling it up and down. We're accelerating it up and down a little bit as it propagates through this wave. As it does so, it creates X-rays. And we've known for a while now that the X-rays that we can create are harder X-rays. They're the same types of energies that you'd be able to see in something like a dental office. And what's nice about this is it's coming from a very small the laser focus. So the X-rays are coming out with properties of spatial coherence, which enables new types of imaging modalities that you can't do with something like a dental X-ray. The other thing that comes out is we deliver this light in a very short amount of time, and the X-rays are also created in a very short amount of time. So now we've made this X-ray beam that has even shorter time properties than the original laser that we used to create it. So this has great applications in terms of seeing dynamics on the fastest time scales. If we want to see chemical or magnetic interactions occur, they happen very, very fast. You need a flash of light that's faster than them to be able to see these things happening as they occur. Our experiment is looking in between the light that comes in to drive it and the X-rays that are produced. Because as it turns out, we don't really understand what's happening in this intermediate region. Depending on the different physics models we use, we might be generating no light in the extreme ultraviolet, or we might be generating infinite light in the extreme ultraviolet. And the answer is probably somewhere in the middle of those two. And so by taking measurements of this light that we're producing there, we can understand which mechanisms and models best tell us what's going on in this type of interaction. And on the plus side, if we are generating lots of extreme ultraviolet light, then this may be a nice new light source for doing experiments with. So we don't have to rely completely on things like large particle accelerators or things like a laser tin droplet source if we just want to produce some light.
So tools like this are really valuable for revealing basic understandings that we haven't confirmed yet.
Right. The modeling is actually very difficult to do. If you look at something like a plasma, there's a lot of atoms that exist in a small region of space. And, there's densities of something like 10 to the 23 particles in just a cubic centimeter. And if you wanted to put all of those particles into a computer, you would then need the memory to even store that. And that 1 cubic centimeter still would require more memory than we have on the planet Earth. So modeling these completely accurately is still far outside the possibilities that we have with current computational technology.
One of the other things I wanted to ask you about was the Strobe partnership. Can you tell me a little bit about that project?
Of course. So Strobe is one of the flagship centers of the NSF, the Science and Technology Centers. And it's a relatively unique center in the sense that it's an imaging science center. Imaging science is very unique in the sense that it doesn't really have a well-defined home, because lots of people do imaging. And using optics and being able to see is such a prevalent part of so many different areas of science that we forget that maybe there's not any place that naturally houses how to do imaging, how to do optics better. And so it can be spread out over different departments, different units, different institutions. You may see it in different locations, and not every place is going to have lots of courses or studies in optics or imaging. And what's special about Strobe is it's looking at how we can make the next generation of microscopes through the understanding of imaging science. And when we put the emphasis on imaging science, it really allows us to do some very novel things that perhaps couldn't have been done in these more siloed mindsets of before. And so, for instance, if you want to take an image of a small thing, you can use a microscope. What makes that microscope? And we have microscopes now that use light. We have microscopes that use X-rays. We have microscopes that use electrons. And so those are all very different things that we can use to take an image. And the I would say, unfortunate way that you may think about it is, well, which one's the best? Which one gives you the best information? And the answer is, well, they all give you different pieces of the image there. And if you have all of them together, you get a more complete picture. And what's more is a lot of the techniques you can use in these different areas can actually be applied, surprisingly, to the other areas. And so that was kind of the realization that led to Strobe being founded and being a successful science and technology center, was that 1 + 1 = 3. And we all gain from doing the sharing of science and sharing of techniques and going for a combined goal rather than our own separate goals.
So one of the last things I wanted to ask you about is you've done a lot of work with community outreach and engagement with STEM. And I just wanted to hear a little bit about how your passion manifests in that area.
In my experience, I'm first generation. I came from a reservation, and then I went to University of California, and I really had little insight into what higher education was, what career options existed. And the big change for me was being able to participate in research, because up until that point, really the media was my only option for understanding what that was. And that was not a very good representation of what it actually means to do science. That was the part that I really loved about it and wanted to go pursue further. And what I find troubling a bit is that we don't really have that experience outside of that in our normal higher education structure. We don't think about learning as this communal thing. We don't think about learning as something that you do in a team, even though almost all science that's being done now is team science. It's done by many people bouncing ideas off of each other, trying different things out. We see this also with how successful centers like Strobe can be, where having many people who do very different things, that diversity of thought can really push the science farther in ways that we'd never be able to do on our own. And that's the part that I'm very interested in now, is how can we take these things that are clearly successful, and evidence backs it up. If you see students who do work more collaboratively, they do much, much better than if they're on their own. How can we bring more of those types of aspects into the classroom? How can we make mentorship be something that's part of the educational experience rather than just being a word we hear? Have it be included as something like professional development? How can we take what we do in the classroom and make it engaging, make it experiential, make it to where you're not alone, you're not forever determined by the outcome of a single test. We really are assessing the learning and providing opportunities for students to learn because they want to learn, not because they're trying to hit some arbitrary threshold. So all of these things I think are just as important as the science itself, and things that we really need to push on in higher education to make our curriculum take advantage of all the great science that we literally see around us and do day to day.
Special thanks to Franklin Dollar and Slava Lukin. For the Discovery Files, I'm Nate Podker. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.